Well, good morning, everyone. My name is Abel Ferreira, and as Edu said, I'm also a PhD student here. And my mission today is to talk about VSC-HVDC converters, and I will try not to be boring. And because this present the history of something sometimes can be a bit boring, so I'll try to just talk about the highest points or the most important points regarding the VSC-HVDC. Just a summary of a comparison between the LCC and the VSC technology. Basically, they have different features. The VSC, in my perspective, they will not replace the LCC technology. Basically, they are different. If you can see on this image that this is with actual numbers. Basically, at blue, you can see the LCC technology, and with the light blue, the VSC. Regarding the power, nowadays, with the LCC, or the line commutated converters, or the thyristor-based converters, you can reach 7.2 gigawatts per converter. And regarding the VSC, only 1 giga, and this is quite recent. This is in Alpha project that is released this year. Regarding the DC voltage, also with as Carlos said, is 800 kV in comparing with 320 kV. So you can see that if you want to transmit bulk amount of power, you just go for LCC, and depends on the application, you can go for the VSC technology. And also this image shows that the HVDC Classic is the, let's say, the name that ABB says to name the LCC-based technology. As you can see here, the losses, the power losses are at a steady state condition around 0.7. And if you see the VSC technology losses are evolving fast and towards the HVDC Classic ones. But still, you have technical limits regarding the semiconductor, so you cannot go, also the cables, you cannot move forward to higher voltages so far. And also you can, as Carlos mentioned, the VSC technology started in '97, and from '97 until nowadays, you can see a great reduction of losses. And you can divide the VSC-HVDC technology in 4 generations. The first generation started with this project. Somebody really from Sweden can pronounce this?
Nobody from Sweden.
Nobody from Sweden. Say again, please.
Helgen, this first word.
Helgen.
Helgen. Grins Jeberi.
Nice. Let's stay with Helgen. I'm saying.
Yeah.
Nice. And this project is basically a demonstration project that was in '97. Basically, it was a collaboration between ABB and the local utility. This one. The local utility had a 50 kV decommissioned AC line over there, and basically ABB used this decommissioned line to transmit power on DC using 2 VSC converters. Plus minus 10 kV on the DC side, and was a 3 megawatt converter. Also connected to an AC grid of 10 kV. I will pass some images with this, let's say, with these converters and with a yellow square. This is the switching frequency that was used for this converter. And as you will see, as we are improving on each generation, the switching frequency will be reduced. So far, will be reduced, and because of that, obviously, the losses will be reduced, and the efficiency will increase. Are you familiar with this type of converter? This is a 2-level converter. Basically, it only has can only produce 2 voltage levels, or plus the VDC minus VDC at the AC output, as Carlos mentioned. And basically you emulate an AC voltage waveform by let's say, by a PWM, and with this PWM we are modulating the AC voltage at the output. And another detail is still nowadays the IGBTs are up to, let's say, 6 kV each IGBT. So in order to reach higher voltage on the DC side, this is not just one IGBT; it's a series of connection of IGBT. So here, instead of having one, you have hundreds sometimes. This was the first generation. 2 years after, this is a demonstration project. 2 years after was a first commercial project in Gotland, and this used a sinusoidal pulse width modulation. Second generation was in 2000 on this Eagle Pass project. Here is in a border between USA and Mexico. And basically why they built this project, during the peak load, this is in Eagle Pass, this is the city between Eagle Pass, USA and Piedras Negras in Mexico. Basically what happens is the Eagle Pass electrical grid is very weak. And so they needed to, during the peak loads, basically, sometimes they had some shutdowns over there. And what they did was build this back-to-back HVDC in order to import energy from Mexico during the peak load. And this project was the first one on the second generation, because also the converter topology, the structure is different. And another curiosity is like, when it's transferring power, it works as, it's being transmitted power over there. And when it's not transmitting power, both converters are operating as a STATCOM. So it's helping the grid to maintain it's providing grid support, maintaining the voltage by controlling the reactive power. This is the neutral point clamped VSC structure. It's the first time that you know that you see this structure. Okay, basically with this structure you can reach one more voltage level. With a two-level converter you have only plus VDC, minus VDC. With this one you have plus VDC, 0 and minus VDC. Basically, if you connect these two switches, you are connecting the AC output to the positive cable. If you connect these ones, you connect the voltage to the AC side, to the DC cable, to the minus DC cable. And if you connect both in the middle, you connect to the ground. From here, if the current is positive, and to here, if the current is negative. And because you have more switches, you have also more carriers to compare with your reference, and then you can emulate this. This type of waveform is, of course, is the output of the converter. Okay, 60 grids, 60 Hertz. This is an asynchronous, as Edu said, this is an asynchronous grid. That's why we moved to HVDC. And also, since you have one more voltage level, you can control better the current, so you can reduce a little bit the switching frequency. So you pass from 195 to 1.5, becoming more efficient this converter. The third generation came in 2006 with the EastLink project. And basically you have here a map of Europe. Each color represents one synchronous zone. Basically, you have Central Europe here, with that is inserted on the same grid. You have UK, you have GB, you have Ireland, you have the Nordic countries, the Baltic countries. This is for synchronous areas. Then you have Iceland, and you have Cyprus, that are completely isolated. They don't have any HVDC or HVAC or anything electrically connected to anything. They are isolated. This project, they move again to the. This project connects Finland here, and Estonia, and was the first HVDC link, or the first HVDC link that connected the Nordic countries with the Baltic countries. And with that, okay, you have some security of supply, because they have more options to transmit power. And once again, on the third generation of HVDC, they returned to the two-level converters. What they did was changing the modulation technique. Basically, on the first generation, they were using the sinusoidal PWM. On this one, they are using, let's say, an optimum PWM. This is an optimizing function that they were implementing. Basically, the cost function was to reduce the harmonics that were produced at the AC side. And with the actual electrical variables, or the converter electrical variables, and with this cost function, what the optimization algorithm said is the right moments to switch. And with that, you can optimize the losses and the harmonics. This was in 2006, it was quite recent. Then the fourth generation, and so far the actual generation, is a modular multi-level converter based technology. And started in 2010. Here we have the more or less a schematic. As Carlos said, was to connect Pittsburgh in California from Portero Hill in San Francisco. This was 88 kilometers DC transmission. And basically this was important because with this cable, they are basically feeding 40% of San Francisco power needs are coming from this DC link. Here is a structure. It's a really different structure when compared to the previous generations. Basically what you have here is a series connection of two-level converters, and with that you can produce a multi-level voltage waveform. At this case, if you see this individual, what is called submodels, is a two-level converter, and in this project in San Francisco was used 400 individual converters, and with that 400 multiplied by 6, because you have 6 series. You see this was a three-phase converter, so you can do the math and imagine how many individual converters were there. How this work? Basically, they were inserting a capacitor. They were inserting or bypassing each capacitor in such a way that was created an AC voltage waveform at the upper valves, an AC voltage waveform at the lower valves, and mathematically, the way out they, let's say, connect, produces an AC voltage also waveform at the output. Here is a generic view of the VSC-HVDC converter technologies. It goes from 97 with Helhun. If you see, is this pixel, okay? And the size of these circles is increasing with the power. So you can see that this Helhun was quite small when compared to nowadays projects. You see at green the projects that are already commissioned, that are already running, and we are talking about 25 projects VSC-HVDC that are running nowadays. As you can see, over the time they were increasing either in voltage power and voltage in power, and also in length, but I'm not showing here. And in blue, you can see that are totally 26 projects that are planned using this MMC technology. And basically, until 2010, we have 12 VSC-HVDC projects with 3 generations. Until 2010, so we are talking about 13 years with 12 projects. From 2010 until 2005, we will have other 13. So you see that in 5 years you overpassed so until 2010, 13, and from 2010 to 2015, another 13. So you can see that in 5 years we did a lot of work about VSC-HVDC. And in the next 5 years, more 26 projects are planned to be built, which clearly says that nowadays the proliferation of MMC is quite high. All these projects from 2010 towards the future than from MMC. Okay, questions so far?
I had a question that is not related with the converters, so maybe
Should.
it's, I mean, not strictly related with the converters. Is like there is a rated power for the HVDC lines. I mean, like let's say if I fixing the voltage, there is a rating power that I don't know, like let's say for AC I can have 400 kilovolts, and I know that over like the natural active power that I can transmit in over long distances is 650 megawatts. Is there something like that? Because this like in what is limiting is that then afterwards are some series capacitors as needed to in order to
Yes,
Yeah,
compensate.
compensate and extend the distance. So is there a rate power, or is I mean the all the
No, basically the things are doing backwards. So you have like the AC grid already done, let's say, and you have something that you want, for instance, in the case of a connection between two asynchronous grids, you have some needs to transmit some power. So depending on those needs, you design the DC voltage.
yeah.
So
but-
you increase the DC voltage in order to transmit more power.
yeah. Okay. Sure. But so there's no physical limitation.
The maximum, yes, comes from the cables, the DC cables, that you cannot go until, let's say, 1 gigawatt. It's impossible. 1 megawatt.
Yeah, with these converters, you can increase the number of
Yes.
levels, but the cable's rating right now is around 320 kV, so they are pushing it to higher voltages. But for VSC technology, I mean,
Yeah.
for LCC, yeah, I think that they are around plus minus 800 kilovolts. So the LCC, it's a bit it's more
Yeah.
mature. I mean, they have evolved a bit more. These things with power electronics like IGBTs, I think that the one is XLP cables are used for VSC technology, and mass impregnated cables are used for LCC technology. So as they are two different technologies, they are still evolving the XLP. So it is quite an technology used for cables for this application. So they are still pushing it. That's the limit on voltage, and the limit on power. It's maybe I don't know the ratings of the IGBTs and the current that you can handle through the cable. But I think that there are around like 2 kiloamps, something like that. That's the benchmark numbers. So plus minus 400 kV and to 2000 kiloamps.
And for the cables, it's just a matter of isolation and putting inside as much copper as I can, because there is no like for the AC cables you have the millican technology. You have you have to perform it like better structure in order to avoid all the eddy currents and everything, right?
Yeah.
So, but DC there is no problem. That's current
Yeah.
flowing.
It's also because of if it happens a fault on the DC side, the cables can, if you increase the voltage, the cables can collapse. Also.
Yeah, I don't know if they have problems with partial discharges or other stuff like that, but we are not cable guys, so
We are not the cable guys.
we are
exactly.
focused
But-
just on converters mainly. So I cannot really tell you why they are not.
But the thing is, if you want to transmit more power, you increase the voltage, and you have to. With these MMC converters, you just put more modules, let's say, but you cannot do because of the cable. So the cable nowadays is what is limiting
That's
the power.
issue.
Do you know if we can turn the air?
You can open the door now.
It should be on. Can you turn it on and
Yeah, it's on.
again. Just yeah. We did that. I did that yesterday, and it started at some point. I don't know. Should be working.
So, may
Yep.
I add one more possible solution for the limit of difference variable power in the DC. As our friends highlighted, that there is a limit on the voltage of the cables, and also we have a limit on the current. We cannot increase the current so much. So one of the I think recent solutions for this is to use superconducting materials in cable technologies. So by this we can decrease the voltage and increase the current so high. I mean, so nowadays we have the cables with a limit of maybe up to 2 kA, but with that technology we will have the cables up to 10 or maybe more kA, but the voltage can be reduced and the isolation problems will be solved. But these cables are very new technologies, and there are some research ongoing on them, and usually they have the problem of cooling. So if these things solved, maybe...
And the price.
Yeah. The price also is still, but I think it's going to be down because there is a strong research going on these cables. So if we have these cables, then the power, I think, will jump up. Like if we are talking now about the 1,000 megawatts or 2,000 megawatts at the maximum, then we will talk about maybe 10,000 megawatts if we need that power. So this is also one possible solution to cross the restriction and limitations.
Superconducting.
Superconductors or superconducting cables. Yeah, that's.
Any question? Okay, so let's proceed for the MMC converter. So once again, you have the each square is an individual two level converter that you connect in series, and you build an arm. Okay, and with 2 arms in series, you build a phase unit, and this is a 3-phase converter. On this case, and this is a one submodel or one element, one square, let's say. So it has only 2 switching positions, or you connect the upper switch and you are inserting the capacitor in series on this series chain, or you bypass, or you connect the lower switch and you are bypassing the submodel and producing a 0 voltage at this output. Depending on the current flow, basically if the current flows like that, flows in the upper diode and is charging the capacitor, if it's flowing from the bottom to the top, is decharging the capacitor, and okay, if the capacitor is bypassed, nothing happens. And one detail here is, if you have, let's say, 400 submodels in series and you need to connect one, basically you are connecting since they are in series, it's more or less irrelevant which one are you connecting. So basically you connect the one that is less discharged if the current is positive, or the one that is highest has the higher voltage in order to discharge a bit. And with that, you can maintain all the capacitors in this arm balanced, let's say. So you are using the redundant states to balance the capacitors. And another detail here. Okay, here you have 3 examples. You have here, let's say, a 4 submodel for an MMC with 4 submodels. Here 3 are inserted. 3 capacitors are inserted. Here is 1 capacitor inserted. No, sorry, it's backwards. The dark one is bypassed. So at the first image, 1 capacitor is inserted and 3 at the bottom are inserted. Here are 2, and here are 4 bypassed and 4 inserted. If you concentrate on this image, if these 4 are bypassed, all the DC voltage at the DC link are sustained by these 4 capacitors, right? So let's say that at each individual submodel, the voltage across it is VDC divided by the number of submodels that are in each arm, let's say. So in this case, the voltage at this capacitor is VDC divided by 4. Yeah, another detail about this converter is like, in opposition to the previous generations, at the previous generations you had capacitors at the DC side, at the DC bus. Here you don't. So all the capacitors are inside the submodels. So it's absolutely mandatory to, so by the number of submodels that are connected, you are setting the DC voltage that are over there. That is over there. And as I showed, this two-level converter only can produce positive voltages at the output or zero. So if you see here, here are the ARM voltages, like multi-level. You have multiple voltage levels at each arm, and each voltage step is introduced by one individual converter. And the thing is, if you sum both arm voltages, you will see that if you sum these two, will equals 1 all the time, because it's the DC voltage. So if you are connecting more at the upper arm, you are disconnecting at the lower arm, and so on, in such a way that the number of submodels per each phase unit maintains constant. And so let's say that the upper arm voltage and the lower arm voltage, they are complementary driven. So whenever one reaches the maximum, the other one reaches the minimum. And the AC voltage produced at the converter output is this one. And another detail is like, if you have, I already mentioned, but if you have, let's say, if you want to connect 70% of the submodels, you connect 70% of those that are more beneficial. So in order to balance all of them. And you see here that you have two references, one for the upper arm and another one for the lower arm, and then the real. If you see here, the red one is the reference that you need for this arm. Then the blue one, the light blue, is the number, effectively the number of submodels that are inserted. And regarding the internal dynamics of the converter, since you have, let's say, hundreds of submodels at this converter, it's normal that at some moment you have everything, and let's say not at nominal conditions. So it's can be normal to have at some moment one capacitor more charged than the other, one phase unit more charged than the other, and so on. And with this converter, also you have internally some internal currents flowing between phases in such a way that you are balancing the phase units and the arms. Okay. And also with these sorting and balancing algorithms inside each arm, you balance all the converter in such a way that you have all the submodel maintained with a normal voltage. And this is absolutely mandatory to maintain the converter operational. And regarding the submodel description, basically this is a submodel that is developed by Alstom. And here is a demonstration project that they have in their installations. And you can see some numbers. Each submodel can operate at the maximum voltage of at 3.3 kV and 1.5 kVA is for voltage and current. But for safety reasons, they decrease the maximum operational voltage and the current. It is one until 2 kV and 1.2 kA. And basically the power, the maximum power that you can have on your converter is a function of how many submodels that you have. And just for physical features, you can see the size. That is 1.5 meters, 65. So it's something like this. One submodel, maybe more, 1.5, 65 by 30. So it's considerable, huge. And you can see here how they are assembled per phase. Okay, And they can reduce a lot this model because they use a water-cooled heat sinks. So if you have a water-cooled heat sink, you can reduce the size, the heat sink, and so on, and you can reduce the overall size of the converter and the submodel. And in the case of Alstom, they are using a tool. They are using a full bridge converter. And you can see here from the real image, the blue part is just a capacitor. So let's say half of the size of the submodel comes from the capacitor. A bleeding resistor. This is just for safety reasons. Once you disconnect the converter, you have a physical resistor there just to discharge the capacitor for safety reasons. For IGBTs, this is a bypass switch. Let's say that you have all the series connection of submodels. And if one submodel fails, just bypass this submodel and you continue the converter operation. Something that didn't happen in the previous generations. If one IGBT blows up, all the converter was shut down. So this is because this is modular and it's more efficient as well. And also, just to conclude, we are also here at CITCEA-UPC, we are also developing power converter solutions, power converters. And basically here we are developing also the MMC. Of course not for the HVDC applications, it's a small scale prototype. And we are doing everything from the scratch. From the single design of a resistor until the overall converter, we are doing everything here. So it's kind of something that you can do also if you come here. So basically you have here the design stage of these PCBs and all the soldering and everything is done here.